And we're back. Welcome back and happy Tuesday. Today, we will finish up our material for the semester, finishing off our discussion of entropy and information by looking at a classification method, decision trees, that have really nice properties that make use of information theory. The reading is on the course Blackboard, these two papers on decision trees, as well as a pretty good one on entropy. So why don't we continue on? Where we left off, project administrative bits. The final project concerns an implementation of the support vector machine problem in its full treatment with kernels and slack variables for soft margins, and that will involve you using the quadratic programming solver to solve the dual formulation yourself and constructing your weight vector and your bias term for your final best hypothesis. You'll be presenting on it on the 4th of May, Tuesday, a week from today, 4:30 p.m. during our scheduled final exam period. Presentation slides will be due same time. Make sure you get them in beforehand, and then the final project work itself will be due the last day of finals, the 7th of May at 5 p.m. So why don't we begin? When we last left off, we talked about Shishini-Jensen-Shannon divergence, which represented a dilation or stretching of this ruler, so to speak, this measurement, this Jensen-Shannon divergence, by substituting the mean with family of means drawn from the Shishini means. And in doing so, you get a much more desirable performance out of your distance metric between, or measure between, the two probability distributions, P and Q, of interest. And then we also talked about Bregman divergence, or F entropy, and with this, we take a convex function and we want to measure the disorder in that function, how wiggly it is, by comparing the constant slope at a point interpolated out in space to the actual rate of change of a function. And this allows you to open up the definition of disorder to a broader class of functions beyond probability. And this is very good with sensed phenomena. All right, so why don't we continue? So let's look at decision trees. Now, a decision tree is a classification method, and it's for learning target functions. And so, like we had in the anatomy of a learner, we have an unknown target function that maps from inputs in your input domain in your raw feature space representation to labels, but it's hidden from you. And so in this case, our label set is discrete, so the cardinality of our labels doesn't necessarily have to be +1 or -1. It could be some arbitrary integer A, positive integer. All right, so the decision trees, there are families of algorithms that include something called ID3, which we'll talk about, and C45, which offers an improvement on ID3. And we'll talk about those in a little bit more detail. But the benefit of these classification models, our decision trees, is that they are interpretable. Once you learn a prediction rule, you can actually examine the prediction rule and follow it. So you can use it for things like medical diagnosis, for credit risk, etc. And so the real value here in decision trees, not only are they good classifiers, but they're also interpretable. You can use it to implement policy that you should follow to achieve some end. All right, so let's take a look. We begin with our label instance pairs, like we usually do in sample points, and our labels are drawn from some discrete set, big K, many alternatives for our labels. So we're no longer dealing with +1, -1. Okay, and so you take your instances and you send them down a tree structure, and this tree consists of nodes, the root node at the top, followed by a number of interior nodes and leaf nodes. And so you issue a series of tests against this input, and when it arrives at a leaf node, you then adopt the class label that you predict for this input based on the majority class label for training instances associated with the leaf nodes. So let's take a look further at this model. Eventually arrive at a leaf node providing the instance's classification. So each node corresponds to a test of some attribute, and each attribute in our vector value representation is going to have instantiations of different values that the attribute can take on. So let's imagine we have the ice input vector, x sub I, and that x sub I can take on a bunch of values. And we're going to call those values j. It can take on the first value, second value, up to including some other value, j. And so here, we're going to mark that as big X, L, j to represent the instantiations of the values that it can take on, at least from the domain over which those individual features are defined. So we take our features, and we list out all the values those features can take on. And so then, for the implementation of a node in a decision tree, we test an attribute's value based on these different instantiations that they can assume. And so we evaluate the values. So what questions do we ask in each node? Well, we say, is for that ice vector, is the jth feature, is it less than or greater than, is it greater than or less than equal to a particular instantiation A from among the set of instantiations that jth feature can take on. And so we have our jth feature, and it can take on value 1, value 2, value 3, and so forth. And that's what we refer to on this previous slide. So now we have this test, and the answer to that test for a given input vector, its jth feature, is either it is greater than a certain value or less than equal to that certain value A from among the different values that that feature can take on. All right, so then how do we perform classification? We have some new input vector in D dimensions, and it's a new pattern or instance. We started at the root node, evaluate test. Now, based on whether this test is true or not, we pursue a branch. If the test is true, we go down one branch, versus if the test is not true, we go down another branch, if it's numerical. But in the case of categorical variables, each one of these tests will correspond to one of the different categories that the feature can take on. And for categorical values or categorical features or attributes, then each category will have a separate branch. And so we pursue a branch for which either the test is true, in the numerical case, or if it matches a particular category for each one of those categorical outcomes, there's a separate branch. And so this process then repeats itself with the next node it comes to for the subtree rooted in the child node of the node we just used as our test. And we do it again and again and again until it comes to a leaf node where it adopts the majority label associated with training inputs that were used to build the tree. So for example, let's imagine this particular network that we built through some fashion, and we'll talk about that. And we have an input new vector, and it consists of 4 features, one for outlook, temperature, humidity, and wind. And let's say we're going to use this to determine whether or not we should go out and play tennis. So we have our new vector, and its instantiation, the outlook is sunny, temperature is hot, humidity is high, and the wind is strong. So we then start out at the outlook node and say, okay, if it's sunny, we go down this left child, and then we examine humidity. Is it high or is it normal? It's high, so we go down this branch. And then after that, we notice from high, it leads down to the majority label, no, we should not play tennis. And so we'll notice here, we pursue this branch with this new input, and the prediction is now, no, you shouldn't be playing tennis based on the instantiation of vectors for this new vector. So then the next logical question then is, how do we construct this tree? That's where information theory comes in, but let's talk a little bit more about these decision trees. And so a decision tree, if you look at all of the root to leaf path, you'll notice for all of the positive examples, we can construct a conjunction for each path from root to node, and then we can disjunct or take the ORing or the union, if you will, of all those conjunctions. And so here we have outlook is sunny, humidity is normal, outlook is overcast, or outlook is rain, and windy is weak, or wind is weak. So if we look at our root to leaf path, where we have a yes alternative or a yes classification, we have outlook is sunny, humidity is normal, yes. Or outlook is overcast, yes, we go play tennis. Outlook is rainy and the wind is weak, yes, we go and play tennis. And so if we take all of the yes answers, the positive classifications, we can actually encode that for this tree as a disjunction of each one of those logical expressions you construct for the root to leaf paths. And so that's exactly what this tree represents, all of those scenarios based on the feature instantiations that give rise to a certain classification. In this case, the predicted class label is yes or no, should you play tennis or not play tennis. So then these sort of problems, this decision tree model, is well suited for certain types of problems. One that is described using attribute value pairs, certainly because we test attributes, where we have a fixed set of attributes. It can be used for continuous or real value quantities by just quantizing that real valued attribute to a number of ranges. And it's better or easier to use when you have categorical. So you can use it for mixed data sets with real and categorical. You can also, works well for problems that can be described as a set of disjunctions of certain conjunctions, where you have a discrete set of outputs, or your class label is finite or countable, and moreover, finite and countable, and your training data probably has errors. How does that work when you have errors in the training data? You can basically take your pool of in-sample points and effectively replace that missing data with the mean. And also, if your training data has missing attributes, you can also fill in those missing attributes based on majority class labels as you go along the way. All right, so decision trees are well suited for problems that share these sort of characteristics. So let's take a look at how you build the tree. Now, of course, how you create the tree is this idea of searching through the space of hypotheses for the best set of nodes and therefore tests that lead to the minimization of some notion of in-sample error. And so we're going to use a greedy search, but we still need some way to measure this idea of what best means. So we're going to begin with something called ID3, and then we're going to improve upon some of ID3's limitations to get the algorithm that is very popular today, C45, which is decision trees. So what does a best tree mean? You need a statistical test that's going to quantify this idea about best. And so this idea then, if best means some selection of tests, we're going to look at the attribute that is most useful for arranging all of your patterns or your vector valued inputs into groups. So you're going to choose the values that you currently have for each attribute. Those are the different values that are going to be the basis of your test, the different values each feature can take on. And so what do you do then? You create a set of descendant or child nodes for each value that can be the possible outcome of the particular variable being tested. And then you sort your inputs based on these tests. So if you said Outlook is sunny, then those instances that have sunny for Outlook, they're going to be pulled together and go to a child node. Those that have overcast, they're going to be pulled together, collected together as a subset, and going to go to another child node. And so essentially, the test results in partitioning your data set into subsets, and each one of these subsets is then sent down to a node that roots the subtree. And so each of these subsets is conceivably smaller than the original. So you choose the values that you currently have for each attribute as possible tests, and then a child node is created for each value associated with the attribute. That's the result of a test. You sort or partition your inputs based on the result of these tests over your in-sample data, your training data. So now, then, this idea is this reduction in uncertainty. That reduction in uncertainty, or information gain, describes how well the attributes separates the training examples into groups that are consistent with the ground truth classification. So what exactly does that mean? When you partition the data based on values of the attributes, each subset should be more and more homogeneous relative to the class label. So why do you make them more homogeneous? Because having multiple alternatives means a higher number of bits needed to code those alternatives. That means higher entropy. So you want to reduce the entropy or choose that particular test on the values of an attribute such that the subsets it induces have the lowest entropy relative to the class label, the most homogeneity relative to the different class labels. So what does that mean? So if you have high entropy, it means there are more possible values or class labels in the resulting subgroups after you partition. If it's low entropy, that means you have fewer different values or outcomes, and that's what you desire. The split that results in lower entropy, therefore information gain. Entropy or disorder is the dual of information, more structure, fewer outcomes. So you have a set of all of your in-sample points, and you have your class labels, and we'll just try this time around with two class labels, +1 and -1. And let's define P sub I as the probability of the ith class label. Now this is general, can be more than 2, but in this case, this is demonstrating 2. The entropy associated with your data set is just negative of the probability of the plus label times the log of the plus label minus the probability of the minus label times the log of the probability of the minus label. So if we add this up over all of our data sets, that's minus the sum of Pi log Pi. And that's the entropy associated with our data set. And so entropy then is used to measure diversity and the level of differences you have within a set of data points as described by the feature instantiation, the value the feature takes on. And this idea of information gain is used as the basis for selecting this best feature value, this instantiation of a feature that results in the biggest reduction in entropy. So reduction in entropy means reduction in disorder. Also, synonym is information gain. All right. So when you gain information, it allows you to reduce or sort the groups of input. And our expression for information gain, SA, we have our data set and we have our attribute, is the total entropy over your data set minus the expected entropy of each one of the subgroups. So here we have a value V, and that V is all the values that the attribute can take on. And so here is the probability of that value is the relative proportion of that subset that you get when you split on that value V for that attribute over the size of the original group before you partitioned into a subset based on that value. And then we have entropy of the individual subset. So this is just the expected entropy of each one of the subsets resulting from the partition across all the values attribute A can take on. And so we have this expression, this is our information gain, and we then select the attribute that results in the biggest information gain, the biggest reduction in entropy, that difference between entropy and the expected entropy of the subsets. All right, and so what does this gain tell you? It describes information about the target function given the value of some attributes. And what this information gain encodes is the number of bits you save when you encode a value in the face of certain information, i.e. the instantiations that your attribute can take on. And so the attribute that results in the most reduction in uncertainty is the one that you choose to split on. And so there's a method called ID3, stands for Iterative Dichotomizer, version 3, and it uses information gain to select the attribute for the test nodes. And so it selects a number of children based on each one of the categorical values or this split if it's real valued, and it searches through the hypothesis space for the set of attributes it tests that coincides most closely with the target function, where coincidence with the target function means that it's the biggest information gain, biggest reduction in uncertainty, so that the homogeneous groups so that the groups or the subsets at the root nodes are the most homogeneous. And that's essentially what information gain gives you. So one of the issues that is in play with ID3, Iterative Dichotomizer, is that it favors attributes that have many values over those that have fewer values. So if you have an attribute A1 and maybe it has two values, value 1 and value 2, and you have an attribute, say A2, and maybe it has 10 values, value 1 through value 10, it will always, ID3, will favor attribute A2 over attribute A1. And so why is that? Well, it's because attribute A2 has a bigger branching factor, or is more quote-unquote bushy. If it's more bushy, what ends up happening is that if you partition your data set based on a test for attribute A2, you're going to be building more subsets that each have a smaller number of data points. Now, of course, if you have a smaller number of data points, by the sheer fact that smaller number of different ways you could have an alternative, smaller subsets means smaller disorder. And so when you compute your gain ratio, you notice here a smaller subset, this quantity probability is going to be very small. And then this quantity is going to be a very large negative number because it's going to be fractional. It's going to be smaller entropy because if you only have 2 examples, that's less disorder than if you had 100 examples. And so when we do that, it's going to favor this portion being smaller, and so your information gain is going to be bigger. So entropy minus a smaller number is bigger versus entropy minus a larger number is going to be smaller. So it's always going to favor a more bushy or higher branching factor for the attribute. So how do we fix this up? We need to penalize for branching factor to make all things equal. And so Ross Quinlan came along and developed something called C45. And it adds a penalty term, namely the split information, which is a measure of the number of bits due to the plurality of values or the disorder due to the bushiness or the branching factor for an attribute. And so what it does is it measures how broadly, how bushy or uniform an attribute splits the data. So this is information gain here, like we said before, and this is called the split information criteria. So you take your original data set and your attribute, and this is just a probability associated with the subset associated with the ith value, or split due to the ith instantiation of that attribute's value. And this is the log of that probability. And so here, this is the entropy associated, or the disorder associated with the bushiness. And so what ends up happening is that if you have more bushiness, this value is going to be larger in its magnitude. And so essentially what this split information criteria characterizes is how many alternatives, as encoded by bits, i.e. entropy, due to the bushiness of, or the branching factor of your attribute. So then what Ross Quinlan does has the gain ratio statistic, which takes your information gain and it divides it by this bushiness, the split information. And so if you have something more bushy, the denominator is going to be higher magnitude, and you end up modulating down the information gain as appropriate based on the bushiness of the attribute. And so what this gain ratio does, it discourages the selection of splits, resulting in groupings that are closer to the uniform distribution. And it also, you can interpret this as a kind of minimum description length criteria. You're penalizing for the description length due to the bushiness. So it's going to favor less bushy splits of the data, which also has a smaller parameterization if you think about the tree. Fewer tests involved. All right, so let's take a look at Weka and actually take a look at an implementation of C45 on a real data set. So I will meet you in Weka. So we're in Weka, and we're going to run the Explorer, and we're going to use the Explorer to pick up a CSV file that I've downloaded already. So I've navigated to load the Wisconsin breast cancer data set. So let me open that. And when I open it up in the Explorer, I have each one of the attributes. There are a total of 32 attributes. The first attribute is the ID. I don't need that ID. So I'm going to remove that from my data set. And then when I remove the ID, I have my target, which is M for malignant, B for benign. That's going to be my predictor variable. So I go into the Classify tab. I choose my classifier. I go under Trees, and I see J48, which is C45 version of Ross Quinlan C45 in Java. So I go ahead, I select J48, And now I'm going to choose my target, my prediction, my class label, and I'm going to use as my class label this nominal value, which is either malignant or benign. I'm going to use tenfold cross-validation set for tenfold cross-validation, and let me go ahead and start it. So I start this out, and I see through tenfold cross-validation my error rate is 5.9 and change percent, so I'm correct 94% of the time. Now, if I look at my tree here, I can see an encoding of my tree. So I have an attribute, let's see, if attribute is less than equal to 2019, I pursue one branch, otherwise I pursue another. If the next attribute is less than equal to 2.654, I pursue versus not. Now you notice here, if I go down this branch all the way to the bottom, I see malignant. Here, malignant, benign. And so this text is an encoding of all of the decisions less than, greater than, or less than equal to. So here, less than equal to 14.96. Here I have greater than 0.1789, and so forth. And so there's my encoding of the tree. And now, if I had a medical data set, I could actually walk the tree for a new patient and tell them what they need to do in interpreting this model to decide policy or behavior or things like that. And so unlike other models like, say, support vector machines or PLA, this thing is actually telling you what the model choice is associated with what the classification outcome should be. And this is our C45 decision tree in the Weka Data Mining Toolkit on the Wisconsin breast cancer data from the UCI Machine Learning Repository. So let's go back to PowerPoint. I will meet you in PowerPoint. So we're back in PowerPoint, and we just took a look at the Weka Data Mining Toolkit's implementation of Ross Quinlan's C45. It's called J48 because it's a Java implementation. And so with that, that's all I had. As usual, please stay healthy, stay safe, and I'll see you all on Thursday.